SwayamPrabha. Digital India. Educated India.
Hello, in this video we will be discussing about Alfrey's correspondence principle. This is a very important principle because it helps us in solving viscoelastic problems, and in solving these we can use the solutions which we already know from the elastic problem. So, instead of solving a new problem, we can rely on the solutions which we already have for the elastic problems, and this will give us a method how to use those solutions in elastic domain and use them to solve problems in the viscoelastic domain. Okay. So, for this we will build up on what we discussed in the previous video, where we discussed about the Boltzmann integrals. So, in addition to these Boltzmann integrals, we also need to know one other concept called convolution integral, which helps us to bring a relation between the relaxation modulus and the creep compliance. So, we will see what is the relation in the time domain E of t and d of t. We will also see what is the relation between these two in the transform domain, means we will take the Laplace and see in the Laplace domain what is the relation between the elastic modulus and the creep compliance. So, once we cover these concepts, we are ready to discuss about this Alfrey correspondence principle, which are essentially a series of steps one has to follow to solve the viscoelastic problem. So, let us start with this first topic, the convolution integral. So, if we have two functions f of t and g of t, we say that convolution of functions f of t and g of t is written as f star g. This we call it as f convolution g of t, or function f of t convolution g of t. So, please do not get confused this with the product of two functions. So, the product of two functions usually we write it as f of t times g of t. This is very different from the convolution between the functions f and g. We will see with the definition how the product is different from convolution. So, here is the definition. We have this function f and g, convolution between them is given by an integral. So, where we have this function f now written in this temporary variable u times g of t minus u du, integral limits 0 to t. So, the difference one has to notice is first function is written in terms of u and the second function is written in terms of t minus u. Similarly, if I now write the convolution between g and f, it is again the integral form, but we will first start with the function g of u times f of t minus u. Now, the question is, are these two related or not? So, meaning convolution f convolution g, how is it related to g convolution f? We see that this convolution follows a commutative property, which means the order does not matter. So, either f convolution g is same as g convolution f. So, whether you move the function first or last, it gives the same result. This is very important, and we will see, especially in the viscoelastic problems, we come across this convolution integral, and that is the reason why we are trying to review this concept of convolution integral. Now, when we take the Laplace transform of this convolution integral, here we are talking about a Laplace of f convolution g is given as product of f and g in the Laplace domain. So, we already know that f dash of s is the Laplace of f of t, and similarly g dash of s is the Laplace of g of t. So, now we have on the left hand side the convolution between f and g, and on the right hand side we have the product. Now it is not, the right hand side is not the convolution, but it is a product, but between functions in the Laplace domain. So we will see one more Laplace. Here we see it is a Laplace between the first derivative of the function f convolution with function g. So here again we can use the same definition of convolution integral, saying that we just replaced f of u with df by du, because we are talking about the first derivative of the function f. So f dash we replace with df by du. But once we apply the Laplace on both sides of the equation, then we get the Laplace as s times the product of f and g in the Laplace domain. So bear in mind, we are talking about integrals from 0 to t, meaning that the load only starts from 0 or later. We are not concerned, or we are ignoring for now the loads which are occurring before time t equal to 0. Only then we can get these s times f of s and g of s. The reason is, if we consider what is happening before time t equal to 0, then these integrals are not valid anymore. So essentially with this convolution integral, where we said this is the definition of the convolution integral, we showed you three properties. First is the commutative property. Second, saying that if we take the Laplace of convolution between two functions, we get the product in the Laplace domain. And then if we take the Laplace of first derivative of a function convolution with another function g, we get in the Laplace domain it is simply s times the Laplace of the first function times the Laplace of the second function, f of s and g of s. Now let us see how we can use this knowledge about convolution integral and apply it to the Boltzmann integrals, which we discussed in the previous video. So here we will try to come up with a relation between the relaxation modulus E of t and the creep compliance d of t. So here is the Boltzmann integral that we derived in the previous lecture, which shows the stress response given by the relaxation modulus E and the arbitrary strain input epsilon. So now with the knowledge of the convolution integral, we should be able to apply Laplace transform for this. So similar to the stress response, we also have the strain response given in terms of the creep compliance d and the stress input sigma. So these are the two Boltzmann integrals we have seen in the previous video. Now let us apply the convolution integral and see how we can simplify these. So here I am just recapping what we have seen in the previous slide, the convolution integral for first derivative of the function times another function g. With this knowledge, we should be able to rewrite this Boltzmann integral as taking Laplace on both sides. This should be written as s times E of t minus s times E of s product epsilon of s. So now we got a very simplified relation in the transform domain, simply because we use this convolution integral to the Boltzmann integral we discussed in previous lecture. Similarly, I can now apply the Laplace transform for the strain response as well. So then I have epsilon of s is s times d of s product with sigma of s. Okay. So, on the left hand side we wrote it in the Laplace domain for the stress response, on the right hand side we wrote it in the for the strain response. Now, let us try to combine these equations. Let us say this is equation 1 and this is equation 2. Now, if I am rewriting this equation 1, it will be S times E of S, and instead of writing epsilon of S, I will introduce this equation 2, which will give me S times d of S sigma of S. Now, if I cancel the stress on both sides of the equation, what we are left out is the product of E of S times d of S is given as 1 by S square. So, this is one result we got starting from the Boltzmann integral, saying that in the Laplace domain, if the product of the relaxation modulus and the creep compliance is given by 1 by S square. But now, let us try to get it to the time domain, so that then we can see what is the relation between the E and D in the time domain. For this, we will apply the inverse Laplace transform. So, once we apply the inverse Laplace transform, we will get it as 0 to t E of t minus u times d of u du equals t, because Laplace of 1 by S square is t. Okay. So, what this integral equation means is, when do we get integral value going from 0 to t as t? This happens when we are talking about integral of simply du. If we are talking about integral 0 to d simply du, then we get it is t. It simply implies that this product E of t minus u times d of u equals 1, right. So, now we are talking about product of the relaxation modulus E and the creep compliance d, but the difference is what we have as the function is not the same. So, for one we have t minus u and for the other function we have it as u. So, what we can imply from this is simply saying that E of t times d of t will not be equal to 1. It is only 1 when there is a time shift in terms of t in one of the functions. This is an important result, because what it means is E of t is not the same as 1 by d of t. So, usually when we talk about elastic modulus and compliance, we in the elastic domain we say both of them are reciprocal to each other, which means E is equal to 1 by d. But here when we are talking about the relaxation modulus and the creep compliance, now we cannot apply the same thing, meaning that they are not reciprocal to each other. This is a very important point to note, meaning that once we get a relaxation modulus, and if I am asking you to find the creep compliance, you cannot simply do a reciprocal and give the solution. So, in the next slide we will take it further and see, okay, we cannot get the relation with reciprocal, but is there any other way to find a relation between E of t and d of t? For that we have to look into the transform domain, which means we will be looking into the Laplace transform domain for the modulus and compliance and see if there is a relation. So, here we are recapping what we already showed in the previous slide, saying that for stress response, when we start with the Boltzmann integral and we Laplace on both sides, we got this relation. How did we get this relation? By invoking the convolution integral formulas. Now, I can introduce E star of S with the definition that it is S times E of S. When I invoke this definition, now I should be able to write this sigma of S equals E star of S times epsilon of S. So, once you look at this equation, you will appreciate that this looks like a Hooke's law which we are all familiar with, meaning that stress is proportional to strain and this proportionality constant is given by the modulus E. But so we are saying this is similar to Hooke's law. Okay. So, we can arrive at something similar by starting with the strain response. So, here we have the Boltzmann integral for the strain response. Once we Laplace on both sides, we get the strain response in the Laplace domain, and again if I now introduce a new term called d star of S, which is defined as S times d of S, now I should be able to write the strain response is simply d star of S times sigma of S. This again is another relation which is similar to Hooke's law. What we are trying to show is we have a very good observation, meaning that in the Laplace domain the stress and strain are proportional, and that proportionality constant is given by either E star or D star depending on what we are looking at. So, which means this allows us to apply elastic solutions in the Laplace domain. So, in a while I will go there, but it is a very important observation that both the stress and strain are related using these E star and D star in the transform domains. So, now let us see what is the relation between this E star and the D star. How can I find that? I can start with, let us say again we name these equations as 1 and 2. I can start with equation 1 and instead of writing epsilon S, I will replace it with the equation 2 which says it is as d star times sigma. So, if we cancel out this sigma on both sides of the equation, what we are left with is E star product with D star equals 1, or in other words E star in the Laplace domain is simply 1 by D star. So, the reciprocality between the modulus and the compliance which we have seen for an elastic problem, that we can see it in the for a viscoelastic problem. The difference is we are seeing it in the Laplace domain, but not in the time domain. So, for viscoelastic problem, E star and D star are reciprocal to each other. Okay. So, this is another very important conclusion we came to, saying that we are now able to relate between the modulus and the compliance, but this relation we are able to show in the Laplace domain. So, using these observations, now we will come to the most important concept of this video, which is the Alfrey's correspondence principle. So, this principle says a step by step procedure about how to solve a viscoelastic problem. So, in solving these steps, we take advantage of the solutions we already have in an elastic problem. So, we do not start from scratch, we start from the solutions in the elastic problem, and then we in series of steps we will see how we can use this solution in the elastic problem to come up with solution in the viscoelastic problem. So, first solve the problem for elasticity. So, meaning you know what is the loads applied on the body, what are the boundary conditions, then solve it in the elastic domain, or applying elasticity find the solution to that problem. Once we find the solution, then what we do is we replace all variables by Laplace transform. But let me elaborate to you what we mean by variables. Here we mean things like strain, stress, your applied loads P, let us say there is a deflection delta, these are all variables. So, meaning depending on if your loading is varying with time, then even for an elastic solution you have this strain is varying with time, stress is varying with time, your load anyway is varying with time, and the response delta or the deformation is varying with time. Then we will replace these variables with the corresponding things in the Laplace transform. So, the stress we will write it sigma of t, I will replace it with epsilon sigma of s. P of t will be replaced by P of s, and delta of t will be replaced with delta of s. In the third step, we now replace all elastic constants with s times the Laplace transform. So, here is one example, Young's modulus E is a material constant or an elastic constant. We will replace this with E star, but what is E star? E star is S times E of S. Similarly, what are the other elastic constants? We can think of Poisson ratio. So, Poisson ratio we will replace it with again mu star S, which is given as S times mu. And similarly, what are the other elastic constants we can think of? We can think of things like shear modulus, G of t will be replaced with G star of S, which is again S times G of S. And similarly, we can come with bulk modulus K being replaced with K star of S, which is again S times K of S. Okay. So, what we have seen is first step, find the solution in the following elasticity. Second, once we have the expression or the final equation, in that equation we will find all the variables and replace them with the corresponding Laplace transform values. And then in the third step we will identify all the elastic constants in the final equation and replace it with S times the Laplace transform of that elastic constant or the material property. And once we have done replacing the variables and replacing the elastic constants, that is when we go back from the inverse, that is when we go from the Laplace domain back to the time domain. So, we do the inverse Laplace transform to get to the solution in time domain. So, we are applying the inverse Laplace to go into the time domain. Once we go into the time domain, that is when we get the solution to the problem in the for a viscoelastic problem. So, let us summarize what we have discussed in this video. We started by defining this convolution integral, where we said this symbol is used for convolution, f convolution g is given by this integral. And later we showed what is the relation between E and d of t in the time domain. So, we said this relaxation modulus cannot be written as the reciprocal of the creep compliance d of t. Later then we said we moved on to the transform domain and said in the Laplace transform is there any relation. There we found that this E star, which is S times E of S, and D star, which is S times D of S, are related by E star is 1 by D star. And finally, once we observed that there is a Hooke's law kind of a behavior in the transform domain, we took advantage of it to come up with a systematic procedure to solve the viscoelastic problems, which we have showed using this Alfrey's corresponding principle. In the next 1 or 2 videos, we will see how to apply these correspondence principles to solve standard problems like analysis of a bar or analysis of a beam. See you then. Thank you.